Alright, web assigned 12E, number 11. At the moment t equals 0, a 25-volt battery is connected to a 5 millihenry coil and a 6 ohm resistor. Part A. Immediately thereafter, how does the potential difference across the resistor compare to the EMF across the coil? Enter your answers in V. So, in this problem, it says that you have a battery and it runs through a coil, so that would be an inductor. Then it runs through a resistor. So the coil is 5 millihenries, so that's 5 times 10 to the negative third henries. Your battery is 25 volts, and then the resistor is 6 ohms. All right, so for part A, we have to imagine is like what is an inductor, pretty much, because this is a RL circuit right here. So an inductor is like a temporary resistor. It resists the changes in the change in current. So it'll be the maximum amount of resistance at the beginning, but over time the resistance will lessen, and then the EMF running through it will reach a maximum value after an infinite amount of time. So if you think about the graph of EMF to time, first let's think about how it is in the inductor. Like I said, it'll start at 0 and then it'll reach a maximum value. So it would be asymptotic at that point. And that point here would be 25 volts. And that is because that is the maximum amount of voltage in the circuit. So it would go something like this, and it would reach that value. Once again, that is for the inductor. Now for the resistor, it'll be the opposite, really. Because, so, in the inductor, it starts off, no voltage going through it because of the resistance at the beginning. So that means that when the at time equals 0, when the current starts, I don't know why I'm doing that. Well, that would be the 25 volt line, and it would be the opposite for a resistor. Instead, it'll be going like this, and it'll approach 0. And that is because in the resistor, at time equals 0, all the resistance will be for the inductor, because that's at the beginning. So that means that the resistance is at a maximum there, so all the voltage will be going through the resistor. And then over time, the amount of voltage going through the inductor will increase because there will be less resistance over time. And so that means that there will be less voltage going in through the resistor. So that's why that one will start approaching 0 over time. All right, so now we have an idea what it looks like, both graphs. So part A, this will be immediately thereafter. So that means that when t is equal to 0. So, again, if you think about it, first for the resistor, once again, since this is at the beginning, all of the voltage will be going through it and not the inductor. So therefore, it would be at the maximum value, which is all the voltage from the battery, 25 volts. So since it's 25 volts going in, 25 volts going into the resistor, there's no potential difference because it's a 25 and 25 going in and going out. All right. And then the resistor, or not the coil, which is the inductor, starts off at 0 because that is when it is resisting the most. So there would be 0 EMF, zero voltage in the inductor. So the the potential difference would be 25. Right? And then for part B, answer the same question about the circuit several seconds later. So this is when time is approaching infinity. So just start with the inductor this time. So it's approaching that maximum value, and so eventually it'll just be 25 volts, and the resistance in the inductor will be, nothing. So that means that the potential difference there would be 0 because there's no change in potential. It would be 25 at that point, and it's 25 from the battery, so 25 minus 25, 0. Boom. And then for the resistor, it'll be the opposite. So now all of the voltage, it is going into the inductor. So that means that the resistor will be not be resisting as much. So that's why after a long period of time, it is approaching 0. And that is why in the resistor, it'll be 25 volts. All right. Now, part C. Is there an instant at which these two voltages are equal in magnitude? Well, if you put the graphs, but just by looking at the graphs, you can see that they're going to intersect at a point. So that's why you know that, yes, they will be equal in magnitude. And then that's so part C. Part D is, if so, when? Is there more than one such instant? All right. So to find D, all you have to do is use the equation that we were taught. But first, what we need to find is the time constant. So in an RL circuit, I'll write it up here. So tau is equal to, in this case, it is L over R, your inductance over your resistance, both of which are given in the problem. So your inductance is 5 millihenries. So he says 5 times 10 to the negative third henries. And then your resistor is 6 ohms. So that would be over 6 ohms. So your tau, your time constant, if you plug this into your calculator, you will get 0.00083. All right. Now the equation that we have to use here that I was talking about is EMF final is equal to EMF naught times 1 minus negative T over tau. All right. So now you plug in your values. So the initial EMF we know is 25 volts. From there. All right. And then your final EMF, think about where these will meet. It'll be at halfway. So half of 25, 12.5 volts. And this will be, on the right side, 1 minus, forgot the E there. That's the equation. Don't forget the E. So that'll be 1 minus E to the, and then it'll be negative T, which is what we're trying to find, the time at which they meet. And your tau is 0.00083. So now what you have to do is plug this into your calculator, and you will get that T is equal to 0.000577 seconds. But I believe they wanted their answer in milliseconds. So in milliseconds, that would be 0.577 milliseconds. If you look at your answer there for part D, that is the answer. All right, now finally, part E. After a 4.3 amp current is established in the resistor and coil, the battery is suddenly replaced by a short circuit. Answer questions A and B again with reference to this new circuit. Enter your answers in volts. So this is just asking for the resistor, and this is immediately thereafter and several seconds later. So, what you do here is, for the resistor, just Ohm's law. You have the current there, and you do have the resistor. And this is immediately thereafter because all of the current is going into the resistor. So, for part E, what's Ohm's law? V equals IR. Your V is equal to, your I was 4.30 amps. And your resistor is 6 ohms. Right, 6 ohms. Plug that into your calculator. You get that it is equal to 25.8 volts for immediately thereafter at time equals 0. And several seconds later, remember how it looks? It'll start up there, but then eventually it'll be less and less, your potential difference, until, several seconds later, by time equals infinity, that will reach 0 volts. So, yeah, that is why your answers are 25.8 and 0 several seconds later. All right. So now for some reflecting. I feel like what was challenging about this is thinking about how the graphs are important in these kinds of problems. You have to understand like how inductors and resistors do behave when put into a circuit, which was a big part of what this this web assign was about. So, but yeah, once you get that, like another thing is the equations. For example, you have to know how to find your time constant, and then of course you have to know the actual equation that we have to use, the one after that we find the time constant. So yeah, I'd say that those things were like the most difficult parts, just having to know how to apply them to a problem. So, but yeah, and we're still able to do the problem, so that's good.